And welcome, everyone. It's a pleasure to talk to you about traceability and standards compliance. You know, sometimes I used to think traceability was a pretty dry subject, but I remember one time being at a conference and there was a gentleman from Mexico from their national authority who was talking about weights and measures, and I was barely awake, and then he said, to bring this home, I'm going to tell you how we make sure that when you go to the pump and you go buy petrol or benzene, when you think you've just bought 19 liters, that you actually have. And he had the attention of everybody in the group. So I think it is a very interesting subject, and obviously standards compliance is one which stands on its own. So with that, I'm going to, without further ado, I'm going to jump in. You may very well also know that we have separately released and are releasing YouTube videos on some of these topics concurrently with these web sessions. So some of you may have been with us the last time where on November 13th of November, we covered the first three topics, and I'm going to do the short review as Luca mentioned in just a moment. Today, of course, we're going to be covering traceability and standards compliance, and we have one more on January 15th, which is going to be an accreditation as well. And then for those people, mostly in the North American audience, who are interested in ANSI Z540.3, we're going to have a session on that in February. I do want to mention that since the YouTube videos, I'm told by the marketing people that the attention span is 10 minutes or less, those don't represent quite as much material as what we're doing in the webcast. So we're able to give you a little bit more of a rich background on some of the key points. But they are very interesting, and they're especially good if you have other colleagues, maybe supervisors, who would benefit from a short treatment on these topics, and they don't have that much time. So just one other item here. You'll see all the YouTube videos. I believe that we make these slide images available afterwards. But if you go to youtube.com/AgilentCalRepair, all one word, you can go take a look at those, and the ones on traceability and standards compliance are now posted there as well. So with that, I'd like to review just some of the key points from last time. And by way of review, we had talked a little bit about when you send an instrument for calibration, what exactly do you expect them to do? And so we spent quite a bit of time examining that. And when it comes down to instruments, really what people want to know is, did you measure the actual performance of my instrument? More specifically, did you do that for every warranted specification? And even more specifically, did you do it for all the options that I purchased? And at Agilent, we try to do that every time. So really, calibration is, did you measure it? And if you did measure it, how accurate were the measurements that you made? That's what I want to know as an engineer. Another point that we took a little bit of time is, if you're in an engineering department, then you're probably, and you're listening, then you may very well be a person who is responsible in your organization for the accuracy of measurements, whether it's a design that's being validated or as part of a production process. So part of that responsibility is calibration. And a lot of what happens in calibration, unfortunately, is not taught in school. And so our point there to you was simply that we encourage you to get involved. And although you want to trust that the measurements were made, really trust but verify. And so we had given you some ideas on how you might do that, but the simplest idea is look at the measurement reports that you receive for your instruments and try to think about, for those instruments that matter most to your organization, in other words, the ones that you really look closely on the data sheet when you buy them in the first place, look at the measurements on the performance tests that correspond to those. You should be getting a measurement report, and that's something that you can look at. If it's something that you want help with, there are folks within Agilent organization that would be happy to assist you to make sure that that your instruments are being properly measured. we moved on and spoke a little bit about the adjustment process, and we had a little flow diagram that we talked about. I won't say too much here because the YouTube video does a kind of a great job of explaining this, but we went through the whole flow diagram of how adjustments are when they're performed, and in particular how important they are if you're in the repair process. Just one slide on this, just a reminder that the screwdriver adjustments are gone. We all remember them, but they've been gone for over 15 years. Kind of like somebody else's children, you're always amazed at how old they are from the last time you thought about them. So maybe the one point to repeat on adjustments was, for modern instruments, those adjustments are automated, they're iterative, oftentimes they're interactive, they move, they branch around, and they require external instruments. Here you see one technician running 2 different stations that are doing adjustments. So, and they can take several hours on some of our highest performing instruments. The third topic that we spoke about last time was measurement uncertainty, and unless you're a metrologist, that is Greek to most people. So that's what I call metrology speak for accuracy, and so that's kind of the code. We talked about the formal definition where it's a dispersion of values that could reasonably attribute it to the measurement. Again, in plain English, that is, how accurate is that measurement? And just on a diagram, I wanted to just repeat this one particular one. If you have a 2-sided specification and you're way out of spec, then everyone knows that's a fail. And if you're way inside, everyone knows that's a pass. The question is always, if you're just inside the specification or just outside, what do you do? And that is where this statistical concept of measurement uncertainty comes about. And in particular, if there's a portion of that that's outside the spec, that represents your real risk of being out of spec. Now, when I talk about traceability today, I'm going to give you some tips and tricks in about 25 minutes on how to read a traceability report. But I want to just remind you, suppose you had 2 different labs, Laboratory A and Laboratory B, and they both came up with the same result and said this instrument for this particular measurement is just inside the specification. You could say, okay, great, we're good to go for another calibration period, whatever you use, 1 year, year and a half, whatever it might be. But really, unless you know the measurement uncertainty, you don't know how good the measurement was. So here, I'm showing 2 different intervals of measurement uncertainty, and you could think of these as standard deviations, and in fact, that's what they are. So if you were to do statistics, that would be where 95% of a population would fall. And just to bring that home, what we're really saying is those areas in red represent the probability that your instrument could really be out of spec. So as you may know, as an OEM, we test extremely thoroughly whenever we build and first ship an instrument. And then even our very best instruments do drift over time. So it is important periodically to make sure that they're still performing according to the warranted specifications. And I'm going to show you an example, as I said, just in a little bit, that you can kind of get an idea from a traceability report, where actually the situation could be as bad as A versus B. And obviously, if someone if you had a situation where the uncertainty was as large as it is with B, then truth is it's really pure luck if you measure the instrument inside the specification. And so that's obviously a very important topic. So the last point in the review is this, that the actual instrument accuracy that you can depend on as a user is not what's in the data sheet. After you get, well, of course it is when you first get the instrument, but on an ongoing basis, after you're receiving it from a calibration, the actual instrument that you can depend on is really as good as the expanded measurement uncertainty of your last calibration. So that's really why that's so important. Okay, so now we're in the new material on traceability. And I like to start with the official definition from the International Vocabulary of Metrology Terms. It's a very good one, and I think it's fairly straightforward. Namely, it's the property of a measurement or the value that whereby you can relate it to the international standard of units. And that's done normally via metrology institutes such as NPL in the UK or NIST in the United States, for example, are two, through an unbroken chain of comparisons, all with stated uncertainties. And I put that last part in yellow, the unbroken chain of comparisons. That's really pretty important. To give you an idea of, so how does that flow work, this is a poster that kind of shows the flow from the very top. You have the Bureau of Weights and Measurements. I think it's in France. And so they are sort of the top authority, and they work with all of the national metrology institutes. So there you see listed CNOM, Mexico, the United States, Japan, Canada, and then of course there are NPL in UK and other authorities in Europe as well. Then sometimes you also have, for example, in the Americas, you have the U.S. Army has their own primary standards lab as well, and many of the ministries of defense in Europe similarly have their own primary standards. The International System of Units, those are the most basic units where everything traces back to those. You see some of those on the left-hand side, things like temperature or length or weight, like that. So this is a poster that's available from NCLSI organization, and I got that from Ryan Fisher. He is the chairperson of the 183 Accreditation Resources Committee. So if you happen to know in your organization, if you have an NCLSI member delegate, they should have one of these, and perhaps you can take a look at it or borrow it from them. If you wanted to get one of these for your office, they don't have it in the NCLSI store that I was able to find, but you could certainly go to their website that I've listed below there and send them a note, and they could make one available to you. All right, let's talk about traceability for DC volts. So what you're looking at here is the we call this the Agilent volt. The most accurate volt that can be generated is using a Josephson junction. So this is across a semiconductor junction, and in order for the properties to work, you have to take it down to cryogenic temperatures, and so that's what you see here. And the gentleman in front of us is one of our, Agilent maintains several of these Josephson junctions. These were originally invented by NIST in Colorado in the United States, but now almost every national authority uses Josephson junctions when they are generating DC volts. Now I want to show you just briefly, if you look, we're looking at sort of a calibration tree, if you will, the primary standard being the very most accurate. So if you look at the measurement uncertainty for DC volts, you see that it's 2 parts in 10 to the -7th. So that's really as a worldwide standard. And by the way, if you're comparing one of these, how accurate is this compared to another one? That's not really a calibration. That is more where you send one around and say, this is what I got, what did you get? So there you can just compare them to make sure that nothing is off wildly, but because they are the top of the traceability chain. The point I wanted to make here is if you take the Josephson junction and you use that to calibrate the voltmeter cal system that we have in that we use for other voltmeters, and there we're using a Fluke 5720 as our main base instrument. You can see the measurement uncertainty there. It's very, very good, but it's not quite as good as what that Josephson junction was. And then if we were to use that very voltmeter cal system to calibrate yet another one, in fact, the very same system, just a different one, you can see how the accuracy begins to degrade each time you change the comparison. I'd like to show you a little bit about microwave power. Obviously, anytime you walk up to an RF microwave system, I, as an engineer, oftentimes think, okay, now how can you prove that everything here is working correctly? In almost every automated system, there's an engineer somewhere who's written a system performance test, and almost always they start with the 50 megahertz reference on the power meter, because that is the closest thing in most instrument test stations to a primary standard. Of course, it's 5 or 6 steps away, but in a given test system, it's the most accurate reference. So we start with, for microwave power, I know at least in the United States, I'm not sure about all of the other national metrology institutes, but I know that NIST and several of the other primary standards labs, what they're doing is they have a microcalorimeter. And so they have a water bath that's maintained at room temperature. And what they do is apply an RF signal, and the microcalorimeter converts that energy to heat. And then so obviously degrees Kelvin is one of the SI units. And so you can very accurately measure temperature, and with proper equations you can relate the power such that you can relate it back to temperature. So that is what you would find. In fact, I'm going to show you some pictures of that in just a moment. So that starts out as a NIST transfer standard, and then for Agilent, we send in our reference standards to either NIST, or oftentimes we send them to the National Physics Laboratory in the UK, who also is at this top level. And that would be our reference, and then from there we use that. We either use that one directly for people needing the highest accuracy, or we will use it for a production working standard, so that when you send one in to our lab to be calibrated, that is the path back of traceability. Just to give you a little photo, here is the microcalorimeter, and this is courtesy of the folks in NIST, Colorado that maintain this. And just kind of zoom in. So this is something that they built specially, and you take this assembly here and you put it into their water. You can see their technician putting it into their water bath, and that is the national standard for microwave power in the United States. Once you've measured on there, then you can transfer that to to a thermistor like this, and then that thermistor, and in fact many labs will send in a thermistor just like this one as their most accurate reference for power. So we see the actual national standard. The first direct reference, again, this would be in a place like NIST or NPL. And then finally, you take that reference and then you're using it in a calibration lab. Now, if for that series that I just showed you of those photos, this is showing you that the calibration factor measurement uncertainty. I think everyone knows that when you send a power sensor in, what they do is over the frequency range, they characterize how efficiently does this power sensor convert power coming in to electrical signal and then to an indicated reading. So the uncertainty is obviously how accurate is that conversion, and you see 3 lines here. So the lowest line in yellow is an actual one for an 8478 thermistor power sensor that was provided by the National Physics Lab, again from the UK. If you then use that to calibrate one of the Agilent 8481 sensors, you get the next line that's just above that. And if you use that the second line there to calibrate another one, then you get the line above that. In each case, you can see that the measurement uncertainty is becoming larger. So that's that unbroken chain of comparisons that we were talking about earlier on. Now, for your own measurements, this is probably a good point to say, how accurate do you need power? All of us, I'm sure, use mobile telephones. So at this point, we all know, you know, when you're in your car, wherever it might be, you get dropped calls now and then, and you say, oh, you know, darn. And that could be any number of things. One of them could be is your cell phone wasn't putting out as much power as you thought. Now, that's generally not so much a critical measurement, and in fact, as we all know, you really have no basis to compare. So, you know, you just wait a few seconds normally, and then you get your cell phone connection again. So measuring power in a cell phone is important, but it's not a critical function. Now suppose that for a moment you work for, I don't know, Ericsson, somebody who's a leader in making base stations, and I didn't mean to exclude anybody. I just happen to know that they have a large presence in Europe, and they make many of the stations there, and also in Canada. Well, so now you've put your base station up 150 meters or maybe 100 meters in the air. Well, when you're up that high, you don't want to be bringing that down for very long, and that base station at any given time is talking to many, many dozens, if not hundreds, of customers. So it's really important that that power be measured accurately. So if you're the engineer that's working on making sure those are in final test, you're going to want to have perhaps this second line that we're talking about. And then let's say now that you're going to put up a satellite that looks over Europe and does broadcast television, and you're the person who's responsible for the path budget to everybody who's going to be subscribing to this. Well, I think if I was the engineer for that, I wouldn't take any chances. I'd get my power sensors straight from NPL. I would not want to mess around. So you can see that depending on your application, you want to be closer to the primary standard, or you can afford to be. And of course, as you get closer, the care that's taken and the price that you have to pay obviously changes. I wanted to show you one flow diagram. This is courtesy of the U.S. Army Primary Standards Lab in Alabama in the United States. But I just happened to walk through their lab about 3 weeks ago, and I was absolutely impressed by a number of things, but in particular, I just loved that in each one of their disciplines, they had one of these posters where you could, this is actually, they have a microcalorimeter exactly the same as what NIST has for the United States. So they start with a microcalorimeter, then they have the direct comparison system, and then from there they're going to an Agilent measuring receiver, and then from that they go to a radio test set. And so you can see each of the levels there that they're using to ensure that when one of the soldiers is out in the field, that they're able to communicate at the appropriate distances away from each other that you would expect that equipment to operate at. So it's a really nice flow diagram of what they do. You know, if anybody out there, if you're a laboratory and you're able to show kind of this sequence, I think this is really good for, they did this for generals and other outside visitors that come through, but I thought it was really good, so I wanted to just show that to you. All right, now whenever you get a calibration from an outside lab, you get a certificate of calibration. Hopefully you also receive measurements, but the one thing that you almost always, well, I've never seen a case where they didn't, you will receive this calibration report. And then as you look a little bit more closely, I'm expanding it here, what you can see is a list of models, what was that instrument, an ID, a certificate number for it, which if you investigate that further will allow you to go back on the, investigate specifically the traceability path. That could be traced all the way back to some primary standard. Now, also, I wanted to just take a moment to show you what I call tips and tricks. So, again, I think all of us have a phone, and these days most all of us have a smartphone. And a while back I switched from an iPhone to an Android, so I went from, hey, I know how to do everything, to I don't really know how to do anything. And there was an application in there called Tips and Tricks, which I was very grateful to see. So I want to just take a page out of their book a little bit, if you will, and show you a couple tips that when you're looking at a traceability report, you may find useful. So let's just dive into that. Here's one. If you're looking on the traceability report and the instrument that you are measuring, in other words, the device under test that you submitted for calibration, is a spectrum analyzer, then one of the tests that is performed is on third-order intermodulation distortion. Now, if you've ever used a spectrum analyzer where you have one signal that's already, could be a large or small signal, and you're doing a sweep over a frequency range, and you're looking to see, is there anything there that you didn't expect, then you are relying on third-order intermodulation distortion. I would submit that almost everybody that uses an analyzer depends on this particular specification. In any case, what I wanted to show you is this. That particular test takes two signal generators. So, just like the old expression, it takes two to tango, well, similarly, it takes two signal generators to check TOI. And so, having said that, if you're looking at I've seen this before, by the way. If you see a trace report on the spectrum analyzer calibration certificate and there's only one signal generator, then you know that third-order intermodulation was not measured. To me, as an engineer, that's a giant red flag because I can't trust some of my favorite measurements that I like to make with spectrum analyzers. So there's a couple ways that you can look through just at the list of instruments to see what was done. Now, earlier on, I gave you an example of two different, I showed you the measurement uncertainty of A versus B, and you might have thought, oh, he's just exaggerating. Well, now I'm going to show you an actual example that I see. I hate to say how often it is, so I won't, but I see this fairly regularly when people show me trace reports. So now what we're going to talk about is a signal generator, and if you were measuring sensitivity, like my earlier example about measuring the sensitivity of a cell phone or a base station receiver, or for that matter, it could be a electronic warfare receiver in the Eurofighter, whatever it might be. If you use a signal generator to test that, and you're counting on the low-level power accuracy to make that measurement accurately. Well, what you're looking at now is a traditional block diagram of a spectrum analyzer. And what I want to just show you is that up until about 8 years ago, everything in the intermediate frequency chain, the so-called IF chain, was all implemented with analog circuits. Okay, so what is the upshot of that? Well, so just zooming in onto that IF section right here, what I want to just show you is every time you would switch filters or change the step gain, and one of the real offenders was, in order to get good dynamic range, traditional spectrum analyzers used to have what we call a log amplifier, where the output is logarithmically proportional to the input. These were notorious for errors, over a dB sometimes. So that's a traditional analog IF section. And one of the latest models that we had, and I see these in calibration labs all the time, is model E8563E. Now, I worked for the Spectrum Analyzer Division for many years, and we were very proud of the accuracy of all of our machines. And this particular model, the 8563E, was the top performing model in its day. But nowadays, when all of our spectrum analyzers have a completely digital IF section, and so There are no analog step filters. Those are all done in with digital filtering. Essentially, there's no error. We don't need all of those step linear IF gains because we have very wide range A to D converters. You see the ADC there. If you have over a large, depending on the bit resolution, you completely eliminate the need for the IF gain. And finally, the log amplifiers are done in the microprocessor. There's no error there anymore. It's incredible. So there's a little product note reference down there, but that it's very possible. And by the way, if the Agilent measuring receiver that you saw in the Army flow diagram, obviously they're depending on a spectrum analyzer which has one of these digital IF ones. So if you look on, I guess the point that I wanted to make here is the following. If you're operating any of the newer high-performance instruments from Agilent, or for that matter anybody else, in your laboratory or in your production test systems, you know, the lab standards that are used in that calibration lab, the only way they're going to be able to measure your instrument properly is if they're at least as good, if not better, than what you're submitting. And the way that you would know that is if you can check the trace report. Okay, I want to talk now about standards compliance, and really in the world of calibration, there are a number of standards out there that you want to consider. Obviously, the one that probably we all know best is ISO 17025, which relates, you know, that you can see from the title. It's the requirements for the competence of testing in calibration laboratories. Obviously, very important. The topic that we talked about last time and the YouTube video 3 is all focused on the guide for expression of uncertainty of measurements. So the first one's quality of your laboratory, competence. The second one, very, very important, is how accurate are your measurements. Then there are, I think, of the second, third, and fourth standards that are listed here all as additional information that support ISO 17025, and I know many metrologists think of them in those terms. So for instance, how do you figure out whether what you measure is a pass or a fail? Well, there's a document, ILAC G8, which is entitled Guidelines on Assessment and Reporting of Compliance with Specification. So let's just dive in. What I'm showing you now is just a timeline of all the different standards that have been out there. And we had a project last year at Agilent Technologies where we said, you know, we want to find out, is it possible for us to use a single approach where we can meet all of these standards at once? And I'm happy to say we were successful. And I'm going to show you just a little bit about what our approach was and what we're doing. So first thing is we had key metrologists, one from Germany in Agilent, and myself and several others, and all of us had open our copies of all of these standards to the critical pages. And then next, once we had figured everything out, just because we thought we had it right, really what you want to do is you then want to check how do the various accreditation bodies interpret those standards. So once we were finished with our work, we checked with all of the accreditation bodies that you see listed there. And so what I'm going to show you is that. Now, I hope it's not shocking, but basically, calibration standards are not perfect. So, for example, if you look up ISO 17025, you type in on Google, you'll see a Wikipedia page. And I know many of my friends, whenever they see something about Wikipedia, they say, oh, great, okay, that's it. And, you know, they are really pretty nice. But here's the thing. They're not perfect. And so, for example, 17025 has paragraphs on very important topics which unfortunately have nonspecific wording that are open to interpretation. So you have to kind of have a buyer beware, or you have to be thinking about, you have to be looking at all of the standards at once to make sure that everything's being done right. One of the key statements in 17025 is when statements of compliance are made, the uncertainty of measurement shall be taken into account. This one causes unbelievable amounts of discussion within the metrology community. And you can see everything from some labs will say, yep, we did that. We got our test accuracy ratio right here to prove it. We're out of here. Well, test accuracy ratio is not the same as measurement uncertainty. So when the accreditation body is reviewing a laboratory, they're not going to allow that. But if they don't look, sometimes that gets used. So that's why in Europe, most of the accreditation bodies enforce that paragraph as show me the 95% expanded measurement uncertainty. And oh, by the way, use ILAC G8 when you're reporting. If you want to claim that you meet 17025, that's generally how that is interpreted in Europe. Just to go back to this label here, really what we're talking about is that you see with the yellow portion there, taking measurement uncertainty into account. Some of it is outside of the specification. How do you account for that? ILAC G8 gives clear guidance on that. So here it is again, and by the way, this is something which if you have interest, you can download it free. And it's only about 10 pages long, if I recall. But what I want to do is just go into, there's paragraph 2.3 is particularly important, so let's zoom in on that for a second. What they do in ILAC G8 is they have 4 different cases where they show, you can see them here visually, and case number 2 is the one that people tend to, it's the one that causes the most angst and discussion. And in that case, it's where the measured result is inside a specification. However, a portion of your measurement uncertainty is outside. And what they tell you is that it's not possible to state compliance with an associated 95% coverage probability. That's what you're supposed to do. So this is the official guidance from that document. And so here's what we've done at Agilent. One of our services is called Agilent Cal plus Uncertainties, and so by that we mean Guide for Expression of Uncertainty of Measurement. And for case 2, what we've done is we designate that as a pass with the double dagger symbol associated with it. And what that means, what the P double dagger or pass double dagger, what that means, you can see the words here on the left. What we've done is we've written the words that you will see in our measurement report to correspond as absolutely closely as possible, if not exactly, to the various paragraphs in 17025 or ILAC G8. So that's the case for when you have a point where you measure where it's just inside. Now I'm going to show you the next one, which is probably fairly obvious. If you measure one that's outside the specification, but a portion of the uncertainty interval is inside, then officially we mark that as a fail, but because there is some portion of the measurement uncertainty inside, we then designate it as a double dagger. Now we've just recently switched over this. This is a new standard within Agilent. So if you look at our measurement reports, right now you won't see this just yet. But I'm letting you know of this because it's work that we're also circulating all within the standards committees. We're hoping that other calibration labs will consider adopting this so that it's easier for all of you to interpret the results that you get from any calibration laboratory that you might deal with. But over the next 12 to 15 months, you can expect that most of the reports, if you order an Agilent calibration with uncertainties, you can expect that this is the symbol you'll see when you have a data point such as what I've shown here. Now, we always measure, some customers are extremely, they need the highest accuracy that they can get. So they don't want an instrument returned back with a pass double dagger, because what that means is that a portion of the measurement, there's a slight risk that the instrument was in fact out of specification. So those customers say, well, you know what, can't you guard band that? Can't you have a tighter acceptance limit for when you perform adjustments? And the answer is, Absolutely yes. So for that one, we call that service Agilent Cal plus Uncertainties plus guard banding, and that's really either case 2 or case 3 that you see in the upper portion of the diagram there. Either one of those is, we mark those as undetermined as received. Now, of course, you don't want to receive the instrument back as undetermined. So what we're really doing is that represents a case like you see in the diagram here. This would be the case 2 that we were looking at earlier on, or normally a P double dagger. So what we do is, to avoid that portion in the red there, we simply we guard band by the 95% expanded measurement uncertainty. That's our limit for performing adjustments. And once you do that, you can pull that instrument back in, and it'll look something more like what I'm showing now. So this Agilent Cal plus Uncertainties plus guard banding is a service that we have for many of our hundreds of instruments actually. And if this is something that you need, then you can, when you're speaking with the Agilent service representative, then you might want to ask for this particular one. It represents the lowest consumer risk. In other words, the lowest risk to you that when your instrument is returned, that it is meeting specifications like it did when it came from the factory. Just one other point on that. This is sort of a summary of, so if you each of these will represent the symbols that we have, and regardless of which calibration you select, I do want you to know that we don't change what we're doing in the, we don't change any of the procedures at Agilent, only the acceptance limits change where we perform adjustments. Let's see, I do want to say just a moment or a little bit about one more ILAC standard. We're going to talk more about this one next time in the module on accreditation. But this is the ILAC policy for uncertainty and calibration. And what I want to just zoom in on here is the key paragraph in this document is really 6.1. And what they're saying is accredited calibration laboratories shall report the uncertainty of measurement in compliance and then with several other ones. So there are a number of accreditation bodies, and I only had space to show 4 of them, but I don't know of any that don't require this. If you're making proper measurements and you want to include the accreditation symbol on the calibration certificate, then ILAC P14 says you will include the measurement uncertainty, and this is certainly something that you should look for, and it's something that Agilent does. So I think I'm going to go, I just want to make one quick point here that regardless of which calibration service from Agilent, we don't change the automated procedures. We don't have a different technician do the work. They don't perform different tests. They do all the same tests, all the same data points, regardless of which one you do. So before we get to questions, I just wanted to real briefly give you a couple conclusions. For the portion here on the compliance of standards, you can really comply with all of the calibration standards with 2 simple questions. And you may hear these from us at Agilent if you're inquiring about calibration. We'll ask you first, do you need measurement uncertainty reported? We have that available for any of our procedures, but we can make it available if you want it included in the measurement report. We always provide a measurement report, but optionally we can also provide the measurement uncertainty if you wish. And then the second question is, do you need guard banding? In other words, tighter acceptance limits. So, and then just one final note on that. If anybody in the audience that's listening today is a calibration lab, then I would also ask you to think about if what you heard today makes sense, then I would encourage you to think about designating the conformance, the pass, and the fails with either the scheme that I showed here or one that's marked, with symbols that are very similar. If we do this, then many of the end customers out there will be better served, and some of the confusion that's out there today about calibration will be minimized. I did a presentation on this in March, and I came in Houston, and the Johnson Space Center, I saw one of the gentlemen in the Cal Lab, and he came up to me a couple months later, and he said, "You'll be glad to know we've changed everything over to that." So I was really thrilled to hear